For this video, we'll be working problem 1 from the study guide. So problem 1 from the end of chapter problems in chapter 3 in Garrett Biochemistry. So the problem states calculating Keq and delta G from concentrations. That's what we're going to be doing. An enzymatic hydrolysis of fructose-1-phosphate, where fructose-1-phosphate plus water is converted by an enzyme to fructose and inorganic phosphate, was allowed to proceed to equilibrium at 25 degrees C. The original concentration of fructose-1-phosphate was 0.2 molar, but when the system had reached equilibrium, the concentration of fructose-1-phosphate was only 6.52 times 10 to the negative fifth molar. Calculate the equilibrium constant for this reaction. Okay, so Keq, and the standard free energy of hydrolysis of fructose-1-phosphate. So delta G naught. So we're looking for Keq, which is going to be equal to the concentration of products over reactants at equilibrium, and delta G naught, which is equal to negative RT ln of Keq. Okay, so let's first consider what the reaction looks like. And I like to do that because I like to know what kind of reaction we're doing. So instead of just saying, some random words, I like to say, what reaction are we doing here? Okay, so first we have fructose-1-phosphate, and fructose is a ketose. And we'll be talking about what a ketose looks like a little later on in the course. But it's a sugar that has a ketone functionality. So if you don't remember how to draw Fisher projections from organic chemistry, you can review that. And we'll be going over those in a later chapter in this course. Okay, so here we have fructose-1-phosphate. And we'll call that F1P for short, okay? And we're reacting that with water. It's a reversible reaction in the presence of an enzyme. We're not told what enzyme. And that converts it to fructose. Plus inorganic phosphate, which is abbreviated PI, and of course looks like this. Okay, and so what did we add? We added water from the water across the bond here. So we added water across that bond, and that's why it's called a hydrolysis reaction. Okay, so we can just abbreviate fructose as F and phosphate as inorganic phosphate. So we're told our reaction conditions are T equals 25 degrees C, which is 273.25, 298 Kelvin. Okay, and we're told our initial concentrations of F1P is equal to 2 molar. And at equilibrium, our concentration of fructose-1-phosphate is equal to 6.52 times 10 to the negative fifth molar. Okay, so we're looking for Keq and delta G naught. Alright, so let's make an ice table. Start by drawing our reaction again as the abbreviated form. Fructose-1-phosphate plus water yields fructose plus inorganic phosphate, and this is a reversible reaction. So if it's a reversible, we can draw an ice table for the equilibrium conditions to help us set up our Keq. So initially we have 2 molar of fructose-1-phosphate, 0 for fructose, 0 for inorganic phosphate, Okay, and then we have, we're gonna, for the change, we're gonna lose, we're gonna have 2 molar minus, I'll just put a question mark here because we don't really need to calculate this. And then we're told we have 6.52 times 10 to the minus 5th of fructose 1-phosphate at equilibrium. Okay, so our change for here is going to be equal to 2 molar minus 6.52 times 10 to the minus 5th, because we know we have 6.52 times 10 to the minus 5th of our fructose 1-phosphate at equilibrium, and we started with 2 molar, so we've gained the difference of this 2 minus 6.52 times 10 to the minus 5th for both our fructose and our fructose 1-phosphate. 52. Okay, and so that's equal to 0.19938, but I'm just going to keep that as 2.0 minus 6.52 times 10 to the minus 5th. Okay. Okay, and then I'm just going to draw dots for that. Keep it simple. Okay. So let's set up our Keq. Keq is equal to, alright, so for each one of the products we have 2 minus 6.52 times 10 to the minus 5th, okay, and 2 minus 6.52 times 10 to the minus 5th over 6.52 times 10 to the minus 5th. Okay, because that's what we have at equilibrium. So the only reason we needed to know that what we started with was because we needed to calculate how much of our products we had at equilibrium. Okay, so our Keq is equal to 613. Okay, and so that is going to be very positive, so it's going to proceed in the forward direction. So our delta G naught we can calculate as negative RT ln of Keq, which is equal to negative 8.314 joules per mole Kelvin times 298 Kelvin times ln of 613, which is equal to negative 15.9 kilojoules per mole. So if we convert that to kilojoules, we have that in kilojoules per mole. Okay, so we need to convert it, so so that's going to give us 15.9 times 10 to the third, because I didn't do that conversion in my notes, joules per mole Kelvin, and then the final answer we have it converted 15.9 kilojoules per mole by multiplying by 1,000. Alright, so this answer is negative, and therefore this is a favorable reaction.